So we're going to be talking about the extent of the reaction, how far the reaction is going to go to reach equilibrium. If K is greater than 1, then that means equilibrium lies to the right with the products. In other words, the bigger the K, the more products will be produced. Make sure that you realize the larger the K, the more products you're going to have. That's going to be important for the next couple of units. Larger K, more products. The size of K and the time required to reach equilibrium are not directly related. And so what I just drew is just showing if it says lies to the right, again, on the right is the products. So again, size of K and time required are not directly related. If I wanted to know how long it takes to reach equilibrium, I would have to look at kinetic data. All K is going to tell me is that eventually I will have a lot of products, or a little bit of products, depending on the size of K. So if the concentration of one of the reactants or products is 0, the system will shift in the direction that produces that missing component. So that makes sense. Normally you start with just reactants and no products in the container, in which case the reaction shifts right to produce those products. Same thing's going to occur if I do not have any reactants and I only have products. The reaction would shift to the left to produce more reactants. Things get more complicated though when there isn't a 0 somewhere. If I have some reactants and some products, I've got to look at the reaction quotient, or Q, to figure out which way the reaction is going to proceed so it reaches equilibrium. So you're going to look at the initial concentration instead of equilibrium concentrations. And there does seem to be a typo on that initial there. So it's going to determine the shift in equilibrium, whether it's going to go left to right or if we're at equilibrium. So Q is exactly the same as K, except it's at the initial concentrations. So when Q equals K, the system's at equilibrium, so there's going to be no shift. If Q is greater than K, then we're going to shift to the left, because that means I have too many products. So the bigger your Q, basically the same concept as K. The bigger the Q, the more products. So if I have too many products, it's got to shift to use some of those products up, which would be shifting to the left. If my Q isn't as big as K, so my Q is smaller than K, I don't have enough products. In other words, I have too many reactants. So it's going to shift to the right, consuming those reactants and making more products. So you don't have to memorize these three if you just remember the larger the value of Q or K, the more products you have. K is a constant, it doesn't change. Q changes depending on how much we have initially. So the bigger the Q, the more products we have. So in this problem, we need to predict the shift in equilibrium. They gave us the K, and they gave us 3 initial values. We know it's initial because there's that little 0 at the bottom, or not. Anytime you see that, it's going to mean initial. So I write my Q expression just as I would write my equilibrium expression. So everything looks the same except it's Q and not K. And I use initial instead of equilibrium. I plug my initial values in. And I solve for Q. My Q comes out to 1.3 times 10 to the 7th. If I look at my K, my Q is much larger than my K, meaning I have too many products. So it's going to shift to the left to use up some of those products. Go ahead and pause the video and try this one on your own. Solving this out, you should have gotten that Q was equal to 0.06. In which case, Q and K are the same, and so there should be no shift. Go ahead and try C on your own, restarting when you have the answer. So here you should have gotten Q was 2 times 10 to the negative third, which is smaller than K, so we don't have enough products. So we need to shift to the right so we can make more products. And again, a shift to the right just means the forward reaction will be taking place. Go ahead and pause the video and figure out which of these will be our answer. Well, Q is less than K, meaning we have too few products. So the reaction should shift to the right to make more products. If it shifts to the right, that means that the forward reaction will be taking place, which gives us A. In this problem, they gave us the equilibrium pressure of N2O4. They gave us the Kp, and we're just solving for the pressure of NO2. So write in our equilibrium expression. And solving for P pressure of NO2. Multiply, square root, and we get 0.6. And since we're dealing with pressure, it's ATM because the other one was an ATM. You did need units since we're solving for pressure, not K or Kp. This problem's a little bit different because they gave us the initial concentrations and we want to know the equilibrium concentrations. Anytime they give you the initial concentrations and you want to find K or the equilibrium concentration, you're going to need to set up an ice table after writing their reaction. So we write our reaction of carbon monoxide reacting with steam to produce carbon dioxide and hydrogen. ICE stands for initial change equilibrium. You could also think of it as RICE being reaction initial change equilibrium. So initially, my concentration is 1 mole over 1 liter, which is 1 molarity. I need to plug molarity or concentration into all of these. And it's said of each component. So I have 1 molarity of everything. My change, my reactants should be going down by some amount because they're reacting. And they're going to go down by the coefficient. My products, I should be making them, so they should be going up. And again, they go up by the same amount since it's 1 to 1 to 1 to 1. So summing that up, I have 1 minus x for equilibrium, 1 minus x, 1 plus x, and 1 plus x. I can write my equilibrium expression. And then plug everything in. instead of saying 1 plus x times 1 plus x, I'm just going to say 1 plus x squared because I have two of them. And then on the bottom, same thing, I'm just going to say 1 minus x squared. It's going to make solving my problem much easier. Because since I have squared over squared, I can square root both sides and get rid of those squares. So I get my 2.26, 1 plus x, 1 minus x. Multiply both sides by the bottom, which was 1 minus x. Distribute. So I get 2.26 minus 2.26x. Is equal to 1 plus x. Combine like terms. So subtract both sides by 2.26, subtract both sides by negative x. And so I get negative 3.26x equals 1.26. Dividing both sides by negative 3.26, I get x is 0.38. And I'll rewrite that so you can see it a little bit clearer. But that's just x. If I look back at my rice table, I see that x is my change. So to calculate my equilibrium expressions, I'm going to plug x in. So 1 minus 0.38, and then 1 plus 0.38. And so I'd write my answer as this written here. 1.38 for my carbon dioxide and hydrogen, and 0.62 for my CO and H2O. And those should have units of molarity on them. So let's look at this one. On this one, we're also looking for equilibrium concentrations. So we're going to have to set up an ice table, but we're going to need to write our equation first. And so we have hydrogen and fluorine reacting to make hydrogen, or hydrofluoric acid. Set up our ice table, and again we need initial concentrations of everything. Looking back at the problem, it says that I added 3 moles in a 1.5 liter flask, and it was of each component. So 3 moles over 1.5 liters gives me a 2 molarity of everything. So my molarities are 2. My change is negative x, and plus 2x. I have 2x because I have a coefficient of 2. The others are just 1x because they have coefficients of 1. Bring that down, so 2 minus x, and 2 plus 2x. Write the equilibrium expression. Write your K. Ignore that K. It should be 1.15 times 10 to the second. And then we plug in our values at equilibrium for everything. We can square root both sides. And here I realized that that was not right. So square rooting both sides, I get 10.72 is equal to 2 plus 2x and 2 minus x. Multiply both sides by 2 minus x. and solve for x by distributing and then combining like terms. So I'm going to add 10.72x to each side, subtract 2 from each side, so I get 19.45 is equal to 12.72x. So x is equal to 1.53. Plug those values into the equilibrium line. And so we get 0.47, 0.47, and 5.06. And again, your units are molarity. Okay, on this one, we're going to go ahead and change that equilibrium constant to a -2, even though it really is a +2. We have the same equation, and this time we have 3 moles of hydrogen in a 3-liter flask, so that's 1 molarity. And I have 6 moles of fluorine in a 3-liter flask, so that's 2 molarity. And I have 0 hydrofluoric acid. So unless it says it, you don't have it in the beaker. Write my change line, bring everything down, and then write our equilibrium expression. Again, for your equilibrium constant, go ahead and make that a -2. The reason being is if it's a positive number like that, that means I have a lot of products. And so x is going to be a large number. Which means to solve this, you would need to do the quadratic equation. If x is very small, because we have a very small equilibrium constant, remember the smaller our constant, the less products we have, the less that minus x is going to matter. So since k is very small, and when we say very small, less than 1, then you can ignore any minus or plus x, even if it's squared or cubed. If it's a minus or plus x, you can ignore it. I cannot ignore the top one because that's not a minus or plus x. So now I have 1.15 times 10 to the negative second is equal to 2x to the second, which is 4x cubed over 2. So I multiply both sides by 2 and I get that. Divide by 4 and square rooting, I get x is 0.0758. Plugging x into my equilibrium line, I get my concentrations of each of those substances. Alright, we're going to do one more together. First thing is our reaction. We're looking for equilibrium concentrations, which says you need to write a ice table. We have 1 mole of NaOCl in a 2-liter flask, so that's 0.5, and we don't have any products. Our change is minus 2x, plus 2x, and plus x. Again, products are plus, reactants are minus. Bring everything down. We'll write our equilibrium expression. Notice K is very small, which means I'm going to be able to ignore that minus 2x. So I've plugged everything in. Again, I can ignore minus 2x, but I can't ignore the square, or the 0.5. Simplifying that on top, 2x squared is 4x squared, times x is 4x cubed, and then I multiplied both sides by 0.5 squared, and so dividing by 4 and cube rooting that, you get 1 times 10 to the negative 6 for x cubed, x being 0.01. Notice x was very small. So 0.5 minus 0.02 is not going to really matter. Plugging that in, you get those values for your equilibrium concentrations.